say welcome and thank you so much for coming. I'm going to kind of offer maybe a slightly provocative title, Queering Computation, because I bet you're wondering, well, what on earth does that mean? How do we go ahead and queer computation? And so I want to offer a number of things that it could mean. Like, one thing it could mean is to make this, one thing that queering can mean is to make strange the familiar. And make familiar the strange. It might offer you the chance to rethink your own scientific practice and how you're using computing in advancing your own scientific work. It could also mean thinking about marginalized people who are in your classroom and how they're learning. In fact, I think it can help you think about how everyone is learning in your classroom. After all, that's what we want to be happening in our classrooms, right? It could help you think about what does it mean to do computation and how does it relate to physics as a discipline. We'll talk about that in a moment. Kind of going out there a little bit more, it could think about incorporating physicality and materiality into students' epistemology. I'm going to use the word epistemology a lot. Epistemology is the study of knowledge production. That is what epistemology means. And another thing that I think most of you who've taught a class or participated as a TA will know that it's not always clear what students mean when they're doing things. And it could also make you think about, well, maybe there's multiple ways to read what students are doing and hopefully push them towards doing physics better. I mean, so that's a little bit about what we might mean by the title. Let me now talk a little bit about who did this work, and there's a bunch of us. So obviously this is me. I'm a professor at Tufts in Boston, despite being originally from the UK. And I've had the great pleasure of working with Anna, who's here. This also took place in the context of a broader project called Remaking STEM. Many of the wonderful people involved in this project, Brian Gravel, Ezra Gouveia, have kind of participated in this. It was funded by the National Science Foundation of the United States and the Research Corporation for Science Advancement, which is a private foundation committed to educational excellence and scientific excellence too. And also I want to just acknowledge my wonderful friend Sabetta Matsumoto, who's a professor at Georgia Tech, who is one of the people that helped me catalyze this idea when I was starting to think about some of it. So as Anna said, I have multiple research programs, and the one I'm going to talk about next week, not in the colloquium slot, but there will be a seminar, is that I study shape. My goal in life is to make shape a computable quantity and to simulate materials that can change shape, often dramatically, and to think about how physics processes from mechanics and stat mech, what happens to those when we put them in an emerging and evolving shape. I kind of describe it as doing cosmology under the microscope, and I'm a theorist, but it's really fun. It's like all of your GR class gets to be used for squishy things that you can make in the lab. One of the things that I've done is created a computational environment, Morpho, that is aiming to help us understand many kinds of squishy materials, and here are some of the applications. So if that interests you, certainly come to the seminar next week. I think it's on the Tuesday. All this is to say, though, Thursday, sorry, yes. All this is to say that I'm a computationalist through and through, and I'm leveraging my experience as a computationalist in everything that follows. So I'm kind of sad that I'm making you sit through an hour of listening to me. I certainly wouldn't wish it on myself. And so I want to kind of just bring it, let's have a bit of a chat to start with. And I want to hear from some of you, how is computing used in physics and astronomy? Throw some ideas at me. Go for it.
I think you have a complex mathematical problem, and at one point you are stuck analytically, so you typically continue numerically.
Bam! That's a great suggestion. So the suggestion is, sometimes we have a model that we can't make further progress analytically, and so we seek numerical solutions. That is a great example. Other examples? Go for it.
The experiments that I run in my lab are far too complicated and rapid to be controlled by hand, and they have to be controlled by hardware that's deterministic with a software stack sitting on top.
Bam. So controlling, and I would actually even say designing experiments, but certainly controlling them. If you're doing femtosecond optics, you are not doing that by hand, right? Any other ways that they're used? So collecting data is a great one. Any other ways? Go for it. Analyzing data, absolutely, and particularly many of us these days are using various ML, AI methods. You know, we might also be doing bog standard fitting as well, but you know, we're using all of these computational methods to interpret data. Okay, yeah, go for it. You look like you had one. No? Okay. Yeah.
But like parameter estimation.
Oh, absolutely. Parameter estimation, like taking a model and trying to estimate. Yeah, bam, love that. Great. Any others? No? Yeah, go for it.
Simulations to like generate data to compare to real life.
Simulations to make data. Yeah, absolutely. Great. Now, is that reflected in our physics classroom? Are any of the things that you describe, which are all great, are any of those actually reflected in how we teach physics? Question.
Data analysis, yes.
Data analysis. Well, that's awesome that that's happening in your classroom.
A little bit of that.
That's not actually happening widely, actually, but I love that that's happening. Yeah. What do we reckon?
Some of our third year classes, we do simulation with fluids or things like that.
I'm not shocked, given that Anna is here and she would not have come to a university where this wasn't true, that y'all are way ahead of the curve relative to the United States, certainly, but probably a lot of physics departments, physics and astronomy departments. So that's awesome that that's happening. I'll tell you that generically, this is not the case, right? So I'm going to kind of make a strong claim here. I'm going to say that computational physics is more than coding. It's often framed as coding, but I'm going to argue that computation is absolutely woven into all stages of physics knowledge production today. It's very hard to look at what physicists and astronomers do and not find computation somewhere, right? And in fact, you already hit on most of these in the discussion. Monash is awesome, but many other universities are not so developed. And, you know, we've tended to think of computation quite narrowly, and it may not even have been integrated. The central goal, I would say, of my physics education research program is to figure out, can we create computational experiences that better reflect these practices that I think we all agree are important? I'll offer kind of a powerful and exciting kind of, you know, efforts to kind of begin to this. Like, there's a wonderful organization called the Partnership for Integration of Computation into Undergraduate Physics with the slightly more pronounceable acronym PICkup. They're fantastic. They offer a lot of resources for instructors trying to integrate computation. But, you know, one of the things that's kind of, I think is sort of clear when you look at their products is they're kind of framing them as being a bit like homework problems, right? Like, here's something that's basically like a homework problem you can do here. It's like simulating charges in a conductor. You know, this is really great, but it isn't being framed through the practices lens that I've just talked about. And so we may not be actually meeting all of the scientific practices. Certainly, that one about experimental running experiments, I think, is a superb one. That is definitely not going to be captured in this. So in this talk, I'm going to kind of, I've got really three objectives. The first thing is I'm going to talk a little bit and make a bit more rigorous the idea of what computation is doing for physics. And so I'm going to develop what I would call a meta model of physics knowledge production. I'm going to talk about a classroom environment, computational making, that aims to make this happen. And I'm going to try and kind of convince you that some of this did indeed happen. And I'm particularly interested in how marginalized students, and specifically queer students, experience this environment. So that's kind of the overall goal. In order to do this, I'm going to draw from a lot of different pools of knowledge. As a soft matter person, I'm already very much kind of interdisciplinary. We're already interacting with chemical engineers and chemists and all of those great people. In my education work, no difference. We're certainly going to be leveraging work from physics education. We're going to be leveraging other kinds of education more broadly, not just within physics, but within STEM making. I'm going to be drawing a lot from philosophy of science, which actually has a lot to tell us about how physicists are doing the things to do. And I'm going to draw quite heavily upon an idea called agency, which is something that's very common and pervasive in contemporary discussions of physics education. I want to kind of make things a little bit concrete. So the first thing I want to do is sort of talk about what do I mean when I talk about a practice, right? Like, and so I'm going to be framing our discussion of doing computation, doing physics in terms of practices. This could include, you know, really a lot of things, identifying phenomena, choosing an objective or objectives for the work, figuring out approximations, simplifications, and so forth, choosing representations that could include visual representations, choosing algorithms, planning, writing, running code, testing, debugging. This is not exclusive, right? The idea of this is to try to ground the work in things that if I were to sit by your side and you would tell me to go away if I did this, like eventually, if I could sit by your side as you're doing science and inventory the things you're doing, that is what would capture this idea of practices, if you like. So we're grounding our work in a tradition known as pragmatic philosophy, which is the idea that we can understand and gain insight into what's happening by actually looking at observable things. I think physicists are quite on board with that idea, and you know, it's a good thing. So one of the key things I want to make is these practices don't exist in isolation, right? If I were to sit by you as you wrote some code, you know, you're not doing that just randomly. You're doing that for another purpose, and you're doing it as part of an active scientific inquiry. And crucially, you may be actually using more than one practice at once. You know, you can be writing code, but also kind of thinking about, you know, well, why am I using a certain data structure, for example? And to kind of capture that, Anna and I created what I would call a meta model, a model of modeling, together with wonderful philosophy of science collaborators, Hugo Boschemann and so forth. And I'm going to just unpack it for you because it's quite complicated. So I'm going to argue that an active scientific inquiry begins with the setting of objectives. And those could be epistemic objectives, the knowledge target that you're seeking. Could be something like measuring a parameter in the neutrino mass matrix, right? That could be an epistemic objective. Could be, and there can also be pragmatic objectives, like I'm going to do this inquiry using particular instruments, using particular resources, because that's what I have, you know. As you're all probably very painfully aware, a lot of scientific equipment and instruments these days are extremely expensive, right? We can't just randomly build a new particle, you know, a new collider just because we want to. You know, we have to go out and kind of make the case for that. So we set objectives. In my case, it might be something like, this is a nice paper that I wrote with my collaborators at UNSW. You know, we were interested in how oil droplets form these fractaline structures. We wanted to understand the physical process underlying this. This is an epistemic objective. And, you know, just because we really didn't want to mess around, we felt it was a fairly simple phenomenon. We were like, okay, let's do it on a laptop because, you know, why not? In order to achieve the objectives, we leverage resources. We leverage literature, data, models, you know, our own expertise. In this case, I leveraged for this paper a prior model of aggregation. We were going to change some of the bits of the model, and we already had the data, right? And then I start doing things. I start producing things. So, you know, writing code, interpreting, implementing, whatever. So we do some production. I made a C code that did the model that we thought. And then having got some results, I then critique them. I examine, you know, does the data meet the objectives of the inquiry, and crucially, the question of whether or not it does is relative to what I would call standards of evidence, things that that decide, in high energy physics it would be something like 5 sigma, right? For statistical significance, that standard of evidence could be really community dependent, in fact. So I go back and forth. Between these modes of production and critique, making changes, and maybe gathering new data, maybe bringing in new resources, maybe even changing my objectives. Sometimes in a course of an inquiry, I might kind of realize that my original objective was not actually the right one. I might want to change it up, And at some point, having gone through a really non-linear process, I'll end up with a program, a publication, a conference talk, some kind of product that then becomes a new resource for future work, right? In this case, a paper in a journal, right? And, so that's kind of our picture of scientific knowledge production, and particularly computational knowledge production. How is that sounding so far? Does that sound like it's resonating with people? Is there anything that you want to kind of pick on, or just kind of, maybe say, yes, I'm liking that, or kind of anything that's sort of maybe questioning? I've hurled around a lot of jargon I appreciate, so. Looking relatively happy for philosophy, actually, great. That's good. And no arguments. Oh my God, if we were in the philosophy department, there would be arguments. That's good. So how the heck are we going to make this happen in a classroom? Because as researchers, you're all comfortable with the idea of this happening in your lab. But how do we make it happen in the classroom? And so we're going to deploy computational making. That's the kind of the environment we're talking about. I'm going to kind of unpack these slightly with reference to education literature. There's a very rich kind of variety. There's a very rich history, actually, in computing education of kind of these open-ended environments. I'm particularly interested in some of the computational thinking and constructionist stuff. A lot of this has been in K through 12, actually. It's worth noting, but has culminated to higher education. And making is a somewhat more recent trend, but I think probably your institution, like every other, probably has ample maker spaces and kind of 3D printers and all this great stuff. Like, it's been kind of a fun thing that's emerged in higher education that centralizes iteration, play, design, and the like. Lest we forget, although it might be fun and look fun, we should remember that, that fun is actually crucial to doing science, because, we're here because we enjoy it, right? And in order to be effective scientists, we need to be creative, right? We need to come up with new ideas and the like. So, these things are kind of, even though they're, they're still, I think, pretty crucial to the design. So what does it look like? If you set foot in my classroom, this is what it might look like. Here are some students, there's stuff on tables, they're kind of picking things up and playing with them and working with them, and they're working in groups and the like. It's low stakes. These are cheap materials. It doesn't really matter what the students do with them. They can playfully explore phenomena. We're using materials really that you can get from a craft store, I would say. And one of the things that's really crucial about the choice of materials is we're not using objects that you might traditionally think of as physics objects like masses and springs and carts and, those kind of things, right? Now, another kind of piece of the puzzle is that this kind of ties into this construct called agency that I talked about. Agency is really the capacity to make decisions, right? It's our freedom to make decisions. So, you know, epistemic agency is like the agency to make epistemic decisions, to choose what kind of method we deploy to answer a question. It can be very macro level, but it can also be very micro level. Agency is so in vogue right now because everyone is trying to reform their labs, and, you know, Anna is an expert in this. You know, so it's a very powerful construct because agency is really kind of the key to unlock the idea of students doing science in the classroom. I guess that's how I might even phrase it. So what do we actually ask the students to do? We give them an open-ended prompt, like make an oscillator. They make something physical, oscillators. They characterize its behavior quantitatively in some way. It could be using their cell phone. It could be using other devices that are available. They build a computational model, and they iterate and reconcile and change the model and change the experiment and really try to find some kind of convergence between the two. I'll show you what that looks like in a minute, right? We have more than one project that looks like this, but I'm going to focus today on the oscillator project just to be kind of respectful of everyone's time. And there you go, there's one oscillating right there. It's kind of nice. Who's in this classroom? Well, one thing that's really interesting is it's an extremely heterogeneous class that incorporates students all the way from sophomore to grad students. It's a very wide range of ages. Theoretically, there are theoretical reasons to kind of see why this might work. The kind of classroom that we're describing is one where hierarchies of power have been rather leveled. And so the idea is that even people who are fairly new to a physics classroom can still have valuable stuff. Yep. Oh, sorry. Yeah, okay. Second year undergraduate. If I say anything that is mired in UK speak or American speak, because I have a bit of an identity crisis going on, just please mention that. So yes, second year undergrad to grad student. It's run for quite a few years. It may even be longer than 5 years.
It's gotta be 6.
It's gotta be 6. Oh my God. Crucially, we have physics, math, and CS majors, and occasionally even more random ones than that. We've had all sorts of people take the class. They do have prior programming experience, but it's extremely variable what that actually means. It's all project-based. It's minimal lectures. Almost all the time is group work. We use teams of 3 to 4 students. We use Slack, which is what I use in my research group, Python and Jupyter. 2 of the 5 projects involve making. The students turn in the code, reports. Everybody completes an individual self-assessment. If people are interested in how we assess this, I can talk about that later. And the data I'm going to show you today is actually from the pre-pandemic implementation. I can tell you a little bit about what happened in the pandemic as well. So hopefully that's relatively clear. So make an oscillator involves, you know, I would say kind of a number of phases. It involves making as many oscillators as you can. We get the students to actually intentionally explore the space a little bit. We get them to prototype and refine. They get their data, they create models, and they reconcile, model, experiment, and iterate. It takes about 5 class periods. At Tufts, we have a rather unusual class length. We have a 85-minute class period, an hour and a quarter, which is, I've never really seen many institutions have that. It's very strange, and we have 2 classes a week. So we're basically talking about like a 2.5 week project. I don't know, what's the situation here? Is it like an hour or?
It's just not fitting.
Okay. I want to be invited back, I guess. This is the point where I would say go ahead and make an oscillator. Those of you who are on Zoom, this is a great opportunity for you to run around your house, possibly engage your kids, if you have kids, and figure out, can we make an oscillator? And I'm kind of hoping that some of you might share some at the end of the course, at the end of the day, sorry. even the end of the talk, get the right timing. This is what we would get people to do. Oh yeah, excellent, awesome. So we already have one here. Can you explain what you're going to do? I love it. You've got a phone. Yes. Out of a phone cable.
I mean, it's easy for you. You can use gravity.
I love it. That's fantastic. And what I love about this example, actually, so for those of you who are at home, one of our wonderful audience members has put their phone cable through the chair, and it's kind of gently swinging. And the reason that I love this is that I think one thing we're seeing here is like this could be it doesn't have to be complicated for some quite interesting physics to emerge, right? I mean, if we were to look at this, we would see, wow, we've got a flexible filament. That's not easy. You know, all sorts of great stuff. You're getting, yeah, exactly, all sorts of great stuff. You see how much fun you can have with this. It's great. Our students were just as joyful, and they made all sorts of stuff, some of which was surprising even to me. They made chaotic pendula. Some of them did make fairly simple pendula, I would say. Most of them not so much. Lots of torsional pendula. Everyone really got into torsional pendula, which I thought was great in some of the iterations. I'm showing you here data from a bunch of different people. I always kind of sneak magnets in because many people are very confused by magnets, and you know, there's eddy currents and all sorts of fun things. And you know, if you have a nice magnet and you have an iron bar, you can have damp. It's all great. It's great. You can see. Someone made a Newton's cable. Oh yeah, we had one student who was so into like his mechanical engineering. He went off and kind of engineered this beautiful kind of ramp. Which is good. And I'm actually going to not show you this one, but I'm going to show you one of the skate park ranks. So we're going to actually talk through this in some detail, just because I want to kind of unpack what's happening a little bit here. So I think one of the things that I was initially very worried about when I started proposing this, I was like, well, will they make something interesting, right? Like I was worried that we would just see a whole bunch of identical simple pendula. And I was like, well, that could be great, but like, would they explore the space? And the answer is yes, or quite organically, they explored the space. So let's see what happened. So because we're education researchers, you know, we videoed everything, we interviewed them all, like, you know, we have a mound of data on this. I'm going to just show you kind of some very, like, really a very projected version. This group emerged in the exploration phase. This central student picked up a little cardboard thing and started rolling some of the magnets, actually. Like their magnetic properties are not really being used, but they're rolling the magnets, and this other student is filming it. Now, these two students on the left and right who participated in this then actually just went off and did their own thing. But some other students joined this central student, and they kind of refined the idea somewhat. So they started trying to think about how can we control the shape of the ramp and kind of slightly improve it. And then they made a third iteration where, kind of having gained some experience with kind of the imaging, like how can we, you know, how can we actually like make sure we're calibrating our stuff? How can we kind of collect some better quality data? And they went, actually, they changed, you'll notice they changed the roller. They went to a different roller as well. So that was sort of, and I should say that not all of these were in the same period. This kind of happened throughout the project, but you know, you can see that they refined their experiment as they went. They also began to envision the model. So kind of in the second kind of class, we kind of invite the students to kind of talk about what they want to do with modeling. They started thinking about what is the phenomenon, like really lock it down. What are the things that we think are important? Report it to the class. Talk about what their goals are, and also kind of relevant physics that they think are important. So, you know, that's kind of where they went. So what they did to build the computational model is they worked in the Lagrangian framework to build it. And they actually reconstructed the shape of the ramp from their video data, fitting a polynomial to do it. So we're all happy they used the Lagrangian framework. Not all of them actually really knew about the Lagrangian framework beforehand, which is pretty exciting. So that was good. So I want to kind of go back to the model here. What we've done so far is there's been an awful lot of production. They have made things, they have gathered data, and they have used a resource, which is the shape of the ramp. Where do they go next? So the thing that was very interesting for this group is that once they had actually produced once they'd actually modeled their system and had predictions from their simulation, it was actually very hard to get it to agree with the physical data. A thing that will shock us not a lot, right? They were able to reproduce some of the phenomena quite well. They got the kind of the damping nicely, but actually getting the particular phase was only possible in some cases. So it was quite a challenge, that proved to be more challenging. Now, what's kind of exciting is that they then chose, what are they going to do? They chose to change their objective, right? They knew they were very time limited, so they changed their objective. They said, no matter how hard we tried, getting the simulated position versus function curve to align with the data was impossible. Notice that that's like an implied standard of evidence there, they're using visual alignment as their standard of evidence. And so what they did is they said, okay, we're going to only care that the total energy at a given point matches the observed data in the theoretical model. And they did that kind of in part due to various visualizations that they deployed. So this thing was from the reports, but if you actually look in their code, they experimented with different representations that might help them unpack the data more carefully. They sort of noted that in the comments of the code, they're analyzing their experiments individually. They play around with the beta term and other constants to fit the simulation, visualizing observed and simulated paths side by side. So it was this visualization that caused them to do that. And indeed, in doing so, they then changed to a new standard of evidence. They said, we're actually more concerned with making the observed data and simulated models share common upper and lower envelopes. So they're actually going to say, okay, we're just going to match the envelope and not the phase. And so again, going back to the meta model, I want to kind of just remind us that this is really quite a sophisticated set of maneuvers these students have made. They produced data and simulation. They critiqued these two things together with reference to an implied standard of evidence. They found they could not meet that standard of evidence, and so they altered their objectives, did new things until they met this revised standard of evidence. Right? So this is quite a complicated set of epistemic maneuvers that the students have made. Now, I want to just note that if I put you in the same environment and I say you do it, you might come up with very different things, and your standards of evidence might be different from these students. I'm certainly not claiming that they did the best possible thing, but I think nonetheless you can see they did something that we can recognize as doing science. Another thing that I want to call out that I think is super cool is that kind of the nonlinearity of this model is pretty powerful. They used the Lagrangian framework, even though it's pretty new to them, as I said, which models the ramp through this height function. And so in order to kind of get the height function, they actually committed what I would call a subsidiary or an ancillary act of inquiry. That is to say, they actually went through like an embedded process where they're like, okay, my objective here is that I need a representation of the height function. And I'm going to have a certain standard of evidence to do that. And I'm going to go through this production and critique specifically to produce this new missing resource, the height function. right? And this is now taking place within the context of the broader inquiry, but it is embedded within it, right? So kind of what I would think of as a more traditional kind of educational picture of what should be happening in our classroom that might see things very kind of cyclically or linearly even, this model is helping us capture, something I think we would recognize as doing science, that is pretty central to how we might do science as physicists. I want to kind of say that I think something that's really probably quite intimidating if you try to do this yourself, I certainly encourage you to have a go, is, well, what the heck am I as an instructor, right? Like, if I'm not lecturing, if I'm not kind of doing the traditional things that an instructor might do. One of the things that I think is really exciting about this idea is that this is inviting you in this kind of environment to be a scientist, to deploy your expertise as a physicist or an astronomer in order to kind of make the doing science happen in the classroom. One thing I want to urge, or kind of really highlight, is that not all of these practices happened organically. Some of the things that I thought would be challenging, like getting the students to code, actually were easy. The students just machined through it. The things that were most challenging are really kind of quantitative measures of agreement. So a lot of students will jump naturally to kind of visual standards of evidence, as we just saw there. Getting them to make that quantitative, to think about something like a norm, think about something like a quantitative fit and kind of the statistics behind that. That does not happen organically, I can tell you. So that's something that we can help with as instructors, right? As an instructor, we can notice and validate interesting phenomena. Like, what's interesting from a physics perspective may not be obvious to the students. And in fact, you can say, oh, that's interesting. Look at that. If I were looking at your wire, I'd be like, oh, wow, look at that curvature, or something like that. You can offer ideas of things to try. If the students are kind of doing something interesting, you can validate that. You can offer resources. And often these are things that you don't expect, actually. So in this class, something that some of the students in one of the other projects got obsessed with is this idea of coefficient of friction. And they wouldn't let it go. And they really wouldn't let it go. Something that I consider, to be honest, to be extremely boring, like unbelievably dull. And I had them coming to me with papers from ancient mechanical engineering journals where they were saying, lol, we have an idea about the mecha, and I'm like, well, how did that happen? They were so engaged that they had actually, done a Google Scholar search and found something. So kind of really cool stuff can happen there. We can also catalyze their reflection and offer feedback and commit them to improvements and achieving excellence. That's kind of crucial. And most importantly, as I already said, being a scientist. This classroom design really offers you the chance to be a scientist in the classroom, which I think is kind of a lot more fun. So the final little piece of the talk, it's not going to be hugely long, but this is another paper. So I've put some references throughout the talk, and very happy to kind of continue the conversation after the question period. If you want to see any of our papers, you're more than welcome. Of course, you also have Anna, who's amazing. I want to just talk a little bit about how queer students experience this class. And one of the reasons that I want to do so is that we know that traditional physics classrooms are not necessarily including everyone. We have ample knowledge of that, right? And, it is, I would say, an open question about how do we design physics classrooms that are welcome and inclusive to a broad variety of people. A group that has been studied very little. I'm one of the people who's published on, one of the few people who's published on this are LGBT students. We find that LGBT issues are intertwined with many other things that are present in physics culture, which are connected with gender and race, for example. So there's a whole lot to say about that. So that's kind of why I'm interested in how queer students experienced it. And we brought a number of I'm a theorist at heart, so I like to deploy theory. So we brought some queer theory kind of ideas to look at the data for this class. One of the things that is sort of crucial to queer theory is this idea of not just having marginalized students present in the classroom, but actually re-examining what we want the classroom to look like. In contrast to some people, I would actually argue that I think that physics classrooms have the potential to be quite welcoming because, physicists and astronomers in our course of our disciplinary lives, we actually have to change our minds very often, right? Because we get new data, sometimes we have to completely abandon. The number of theories that I've come up with that did not survive data is a very sad pile, I can tell you. Some of them I cherish very, very greatly, but what can you do? So actually, the possibility, if we lean into our identities as physicists and astronomers who are open-minded and responsive to data, there's the opportunity, actually, that we could do this. And again, agency, the students having control over what they're doing and the disciplinary decisions they're making, I think is a pretty key ingredient. Now, I want to kind of highlight this because one of the students in the class, Emerson, by the way, the names are anonymized. They're changed. This is not their real name, but they discussed how the disciplinary identity was important for their activity. And I want to kind of note that they were not a physics major. They're a comp sci major. And they sort of contrasted the climate in comp sci with the climate in physics. They sort of said, in computer science, they would not go to the professor. They would always go to the TAs. I don't know to the extent that that's true in Australian higher education or in other universities necessarily, but that was the case. This is what this student reported. So they said, basically what they're saying here is the support network is the TA network. And then they said, okay, but this didn't work for me because they had gone to a TA before. I went to one and then they were discriminatory against queer people. And I was like, well, fuck it, I'm done, right? And that's a concern, right? So this support structure that was, that the CS department has invested heavily in trying to, that we want it to be a good thing, was not working for this student. They sort of reported that their choice to participate was actually therefore mediated by what else was going on in the room, who was there. And they particularly referred to Ashley, who was another student, as a source of comfort. And actually, Ashley's presence kind of facilitated their willingness to speak up and participate. So it just depends how much of a community you have in the class at a certain time. And this is something that we are still trying to understand. I think it's a complicated and nuanced kind of discussion about kind of how these sort of social factors, how these climatic factors are working in our classroom. They noted that, Emerson kind of noted that working with Ashley worked really well, and they kind of felt this sort of balance between chaotic energy, as they put it, and Ashley being very stable. And then Ashley would be like, okay, let's just do this. So this is kind of really interesting as the project continues. We're going to try and understand how these sort of group identities and group processes form foremost. And what's really great is they actually started talking about agency and the like. Ashley said people would take their piece of the project as far as they wanted to go. That's what we want to hear. And also talked about kind of mutual reinforcement between the groups, like, different, if another person came and said this is a cool thing, we'd like, cool, that's great. So kind of, again, this is helping us think about, how these factors might be working in our design. I want to kind of add a brief coda because we're nearly out of time, because you're like, oh my God, how the heck did this work in the pandemic? And much to my amazement, genuine amazement, the answer is shockingly well. I don't know, if I never have to give a lecture on Zoom again, it'll be too soon. Zoom is terrible for lectures, but it actually works quite well for small group interactive work, The US postal system is never super great, but totally collapsed in the pandemic. I was hoping to be able to mail materials to the students, but I couldn't because it just wasn't happening. And so instead, the students actually found their own materials. For example, this group actually, I love this one, they actually found like a piece of public art and started rolling like a ball they found in it. And as you can see, actually watching it, there's some really interesting physics going on here. And you bet that they modeled it and kind of discovered all sorts of cool things. The point was that, that this is really a great topic for a separate talk. You know, the fact that we had this very careful understanding of what we mean by doing science from our meta model means that we're actually, I think I can say with some confidence that we actually saw the students making essentially the same epistemic maneuvers. And that actually shifted our thinking, because prior to the pandemic, I and collaborators, we had felt that the materials that we provided were really crucial elements of the design. And maybe that actually isn't so much the case. It's kind of changed our view. So, exactly on time, I am going to offer some conclusions. I'm going to say that if you take a computational physics environment and you introduce making, you're offering the chance for students to engage in modeling and connect their models with reality. I would also say really doing physics, right? We have, I hope I've given you just a flavor of the evidence we have. I just showed you one group. We have many data pieces, many groups to look at, and some of those are in one of the papers. There's more papers to come. But the idea is that, you know, that making is an environment that is enabling students to acquire things that you or I would do in our normal scientific career, but are not necessarily clearly or obviously included in physics education. And if we have any concern that if we offer students agency, will they do it? Will they take it up? You know, are they too bored or too, like, you know, busy to do it? Oh my God, they run with it. In fact, they run with it even further than I think we expected. They do it in their choice of objectives, features of the phenomena, what they're interested in, and even their standards of evidence. And yet, what I'm showing you is not even the beta product. I think it's the alpha product, right? And as such, there is so much left to understand and how we look and optimize these environments. And I will therefore just simply close by thanking everybody who's been part of remaking STEM. So thank you for your attention. I look forward to a little discussion. So, thoughts, ideas? Go for it.
I have a question. You spoke a lot about agency for the students in your talk, but I just want to hear how you went about them choosing groups and things like that, because you spoke a lot about groups.
Great question. So the group, I think we've certainly, I think a posteriori, we're seeing just how important group work is. A priori, I included group work because it's the #1 thing I get told by employers that they want our students to be able to do. They want to work with other people, right? It's really hard, right? We have groups of 3 to 4, because that's a recommended number. We use a bunch of different strategies. So in the first part of the course, the early part, we will have students identify kind of their disciplinary backgrounds and try to ensure a diverse team. We need to make sure at least someone in the group has familiarity with Python. And we also would really like to have a nice combination of disciplines. Sometimes we allow the students to completely freely choose. Other times we're strategic and kind of help pick them. We're going for the criterion that students in their future careers will have to work with a variety of people, and that it's valuable for them to have experiences of diverse teams in order to do that. Recognizing that if we're bossy and tell them exactly what to do every time, that actually it's good for them to have a little bit of choice if that kind of helps. So we actually deploy, we have quite a complicated strategy there, and it's a different team every time. I really wanted the students to have as much experience. I always tell people, like, for the second and third projects, work with someone who you haven't worked with. You know? Thanks for the question. It's a very crucial point.
I was thinking about it because all of my group work experiences with the groups were chosen for me in undergraduate were really negative experiences.
Many students come in with negative prior perceptions of group work. This is a major barrier. And so I do two things. The first thing that I do is we have a conversation about why we're doing group work. A lot of it comes from, like, a lot of this course actually was inspired, but I went to observe companies in Silicon Valley, right? And I went and sort of talked to Google and Meta and all this, and I said, what do you want from your grad student? What do you want from your students? They said communication and group work, right? And so I sort of in the class, I explicitly talk about how group working experiences are going to benefit us as scientists and professionals. And secondly, we kind of collectively come up with best practices for group work and things to avoid as well. We even make a kind of on the blackboard, we make like a contract about what are we going to do and what are we going to avoid doing. So again, there's framing to kind of support group work. And I'm not going to claim it's optimal, actually. I think that is a very important topic of future research. Other questions and thoughts? And also very welcome to have some from Zoom. I apologize. Yay, okay, so just if you see a question, feel free to ask it. Okay. Any other thoughts? Go for it.
So my question, I'm sure you've had versions of it before. I teach first year physics here, so this is the sort of context of my question. And let me preface it as well by saying this class was like so much fun to take. But I have a class with way more students. I would guess that the ratio of instructors to students, and with respect to the TAs in my class, enthusiasm level for...
Oh, I teach intro classes too, although yours may be bigger. Mine are pretty big.
It's more than 27. And you also, it's in some sense looks like there's a selection effect. You have sophomores who can do Lagrangian mechanics, but in a several hundred student class, you'll have first year. You don't have always strong students. You don't have a lot of resources.
So I think the question may be, how do we get this kind of thing to happen in an intro environment? Yeah, great question. Oh, my God, are we time poor? So let me kind of emphasize that what I've presented today is what I would call, as an education researcher, design research. We are trying to understand how the things that we do in the classroom are designed. How do they translate into learning and disciplinary activity? What I've shown you is effectively my lab for education. Does that mean that you need to reproduce my lab in your intro classes? No, absolutely not. And I would not do that either. What I would urge you to think about, however, is think about the scientific practices and the model of modeling that I've shown, and think about where in my intro class are there opportunities to foreground some of those things in a way that I might not do. For example, in my intro class, is it possible that students could engage with data and theory? Like, could we do that even if they don't collect it themselves? Is it possible that we could even have a conversation about how scientists do science, right? The labs are a fantastic place, and you already have amazing, I love the environment downstairs. It's really fantastic. Connecting between what's going on in the classroom and the lab component, there's a lot of opportunities, in fact, for that. Or you could even have an out-of-class project or something you do over the... So I think there's lots of ways to deploy the idea of doing science in the classroom that is gonna kind of scale. And this is very much something we are interested in as well. Does that kind of maybe get at it? Please.
So the idea of agency I thought was great.
Yes.
And it appeals to me as I can see how that's actually how we all, get the best of our learning. any advice for that in particular in that kind of mass physics setting where you're on a tight schedule, you need to get these concepts, you have a range of ability.
I think number one, talk to Anna would be a good thing. But I think, again, I would think very carefully about, are there places, like I would think about doing maybe 1 or 2 or 3 very intentional activities. I mean, one thing I do in my intro classes that I think was really motivated by this is I used to show a demo and we'd talk about it. And I completely changed up how I did that. Like, instead of me showing the demo, the students would have to predict. Firstly, they'd have to tell me what should the demo be, and I would make it happen. They would have to predict what was going to happen. It would happen. They would be like, oh, it didn't do that. And then we would go back. So we would even though they're not necessarily doing all the stuff themselves, there's still this idea of we're having a scientific conversation. And there's a really great moment that we have on video, if you remember, where the students suddenly were like, no, but you have to do this. It was with a Van de Graaff and some blobby things. And they were like, no, you have to do this. Put the blobby things on the Van de Graaff. And as an instructor, I did that, but I said, okay, well, what do you think is going to happen? And they had to commit to something beforehand. So I think there are ways to leverage these ideas that are scalable and small and fit within. We now have, since you left, we now have like nearly 500 intro students in our class, and it's challenging to do this stuff at scale. At the same time, I have been into a classroom at Georgia Tech that had 800 students, and the instructor said, turn to your neighbor and convince them you're right. And every single student in that class was engaged and participating. So I really do think it's more possible than we might suggest. It's hard and skillful, but great. Thank you for the question. I really appreciate it. Yeah.
I have a question that kind of tied up with Maria's, I think.
Yeah.
If you ever had the experience of a particularly introverted student where working in group is not their cup of tea.
Right.
And it's true that Google and the likes will require some certain skill set. But it's also true that one can also not work for Google and have opportunity.
I would actually not recommend it, with no disrespect to friends who do.
Yeah, but what I mean is that you might find a quiet job, and there are people that are introverted. And did you ever had an experience with people that actually did not find this?
Well, one thing that, so absolutely, I think one thing that is definitely something we've been working on is that, when in the early days when we first did this, some students would jump in and take to it like a duck to water, and others would actually just be horrified and unable to do anything. I don't know that introversion is necessarily the right theoretical construct to analyze those things, but we definitely have seen differences in students' willingness to kind of participate. And one of the things that we've done to try to mitigate that is to lower the stakes and kind of structure the activity, so that there's more than one route into this. So if there are students who are maybe not taking it up, there's something that they can do. We'll actually offer them things and be like, well, you want to try that? And it's actually okay for them to work on their own in the initial phases. Well, we actually do sort of emphasize totally great to explore things on your own for a bit, and then maybe we'll kind of loop them together a little bit. So I kind of think about, there's going to be multiple pathways to doing this. I mean, many of us, I'm actually an introvert. I might not seem like it, but I certainly am. I have to go lie down after talking with people. Many students are introverted, and that's totally okay. We want to think about, again, with this sort of idea of, diverse pathways, how can we facilitate this?
So would you think that this actually helps to get out of your shell more than actually intimidate? And
I think one of the phrases that I think Anna kind of deployed, maybe in a slightly different context, but is kind of maybe productive discomfort, right? Like, it's actually okay to feel a little uncomfortable, whether it's because of the social environment, whether it's because of the material, whether it's because of the concepts. We want the students to feel like, we want the students to have that experience because we all have it as scientists, right? As I tell people, 90% of the time I'm wrong, or I don't know what is going on, so I think that that's kind of something that I think actually in itself, that actually is kind of a goal of the environment, but it requires careful support. And again, it's something that we have refined, because I say initially when we first did this, we would have this kind of, most of the students loved it, a few students were just very resistant. Over the years, as we've tried to offer support and pathways, I think, we're not seeing that anymore. Yeah, it's a very good question. I know people have to run, so feel free to run if you do it. Yeah, go for it.
Love the talk too, learned so much. Thanks.
Thanks.
Particularly like the fun at the centre of it, because it's
why are we all doing this stuff? Yeah.
And it's something that I think, unitised mass higher education just drains the fun structurally out of things, and it's our job to try and pour it back in. So I have a very unfun and boring question.
Please.
About resourcing, which is, when we've tried to run project-based learning before that's been open, that's at least somewhat open-ended, less open-ended than what you have. And in a teaching lab environment, practical exercises, it's been very TA intensive. So we've had, 3 TAs catering to 4 groups of 4 students each.
Oh, we never have anything like that.
Students in total, so most like students just didn't get to participate.
Yeah.
And that was essentially ran it for years on a selective basis, and it wasn't sustainable or scalable. How many TAs, how do you pair them? They have to be good at pedagogy as well as broad in physics here. It's a challenge.
I love this question. I think resourcing design is like absolutely essential. So what I think what I can say is that the first thing I can say is that we have, it's generally been about 30 students, and we have sometimes but not always had a TA for that.
So sorry, we is then just you?
Me, yes, just me and a TA. Sometimes I've done it on my own.
Wow.
Yeah, we co-taught it, which was, I think, was sort of, it was delightful. It was really fun. I think that was my favorite iteration, actually. This is a class that co-teaching is really good with. So haven't always had a TA. There are several things that are helping us with the scale. The first thing is the grade, the feedback really is per group rather than per individual, right? So that really helps the time efficiency. And secondly, like I find that one person between 30 means that I can get around the class at least once per class, and that seems to be about enough. So I think I think a ratio of 1 to 30 students is probably what you want to do. When we've had TAs for this particular course, they've always been kind of very engaged, people. Generically though, so one thing that we've done at Tufts, and Anna actually kind of designed a rebooted version of this, is we actually have a course on pedagogy that's like 1 credit. I don't know, again, how the credit hour system works here. I bet it's another do not talk about that. But, we have a 1 credit hour course on physics pedagogy that all TAs are required to take at least once. And as a result, I can actually say I have seen like a real sea change in the quality. Like, I mean, honestly, the TAs are often asking better questions about pedagogy than I'm able to pose, And so if I were to kind of scale this up to the next level, I think I could easily draw up, I would probably hire undergrad learning assistants or have a grad student. And I think that ratio that I've described is okay. I haven't tried to do that, and that in itself is an exciting research project, actually. Again, I want to emphasize that because this is design research, you don't have to recreate this environment, and you absolutely shouldn't, actually. You should do whatever it takes. I can see how this could be, we could deploy things like this in different environments, kind of, again, being attentive to the resources. But it's a very important question, and thank you for it. Okay, I think we're probably all ready to grab a tea, which is wonderful. And thank you again for your attention. So I really appreciate the audience. And for those of you on Zoom, thank you so much for participating as well. Really appreciate you being here. I know it's not the easiest week for everyone, so thank you.